Kia ora koutou, nau mai, haere mai. Welcome to lesson 7 for introductory physics. This lesson is going to start the forces section of our course. In the first two sections, we learnt some of the tools. We learnt about basic motion, looking at kinematics and movement with constant acceleration. As we've mentioned, though, we haven't talked about the causes of acceleration yet. So what causes objects to move, and that's where we're going to start today. So our lesson is just on forces. We're not going to get into too much math yet in this first lesson. We will mention some vector stuff at the end, but we're not going to get into too much equation or math stuff yet. The goals are simply to understand what we mean by forces and interactions, to understand free body diagrams, which is just a way that we visually represent scenarios, and then introduce, as I said, a little bit of math, but not much, some net force concepts, which is to do with vector maths, and then equilibrium definition at the end there. So first of all, what are forces? What's a force? Now, so there's this old joke, how do you make a sausage roll? You push it, right? The concept of pushing something to make it move, that is what a force is. A force is just a push or a pull on an object in order to try and cause motion. That's all a force is. I say try because it might not always result in motion, as we'll see. But a force is just a push or a pull on an object. That's it. When we do manage to cause motion, then that's going to be a change in velocity. So if something is at rest in your frame of reference, remember you can choose any frame of reference, but if you choose one where the object is at rest, and then you apply a force and make it move, then its velocity will have changed in that frame of reference, therefore it has undergone an acceleration. And because the frame of references that you choose can't be accelerating, right? Remember that any frame of reference has to be just a constant velocity frame of reference. If you choose any frame of reference, then apply a force to that object, its velocity must change in that frame of reference as well. So even though you can choose one where it's stationary, if you choose any frame of reference, then an applied force that results in a change in motion is going to result in an acceleration. So in general, forces cause acceleration. We'll get more into detail on all of these definitions as we go. So what actually is a force? Some people struggle with the concept of a force. A force is not a thing. An object can't be a force. The idea of a force is the exact same idea as that of a push or a pull. Right? You can push an object, but you can't just hold a push. You can't have a box of pushes. You can't have a box of forces. Right? You cannot just get a force. A force is just an applied force. It's an applied thing to any object. What a force is a vector. It's a vector because it has a magnitude and a direction. If you push on something, then you're pushing it in a specific direction and you're applying a certain amount of force. If you want to push harder, you apply more force. Push a bit less, you provide less force. If you push at a different angle, you change the direction. So a force has a direction and a magnitude. A force is a vector. The entire next lesson is going to, no, sorry, not the next one, the one after that is going to talk about common forces, but some of the ones that we're going to talk about are gravitational attraction, so force due to gravity, the normal or support force between an object and whatever is stopping it from falling in towards the center of the earth, and friction is a very common one when you have two objects that are moving past or against each other, and that does include air resistance, so air resistance is included generally when we're talking about friction. A lot of the time when you're thinking about a push or a pull, we imagine a person or a being of some kind physically pushing on the object. That's known as a contact force. Anything where you have to make contact with the object to apply the force, whether it's a push or a pull, that's a contact force. But one of the most consistent forces in our lives is gravity. The force due to gravity, the attraction between our body and the earth, or any object and the earth, is a force at a distance. The center of the earth and the center of that object aren't actually touching each other. They're not connected by some big spring that's pulling them together, but they are attracted to each other. So that gravitational force is known as a force at a distance. In the second half of the course, we'll learn more about another type of force at a distance. But for now, we're just going to, gravity will generally be the only force at a distance we're going to think about. The other definition that we want to cover during this lesson is interaction. So interaction in general everyday life can be all sorts of things. In physics, it's explicitly a process where two objects interact in some way that results in a force being experienced. So the interaction requires a force being experienced as its result. That's what interaction means. Any kind of interaction in everyday life is only a physics interaction if there's a force involved. With the Earth, we're constantly interacting with it, so we're constantly experiencing that gravitational force and thus that acceleration due to gravity. Whenever you stand or sit on a surface, so whatever you're standing or sitting on right now, that object is stopping you from falling in towards the center of the Earth, whether it's the Earth itself or whether it's the chair or a floor or whatever. That object is exerting a force on you in the opposite direction to gravity. One away from the surface, that's stopping you going into the surface. And when you push on an object, then you are providing a push force to that object. So as I said, even just sitting in a chair, you're already experiencing a whole lot of forces. And of course, there are forces inside you. There are countless forces inside your body. You've got muscles pulling on tendons and pulling on bones, and the skin force, sort of a tension force holding that skin around your body so that it doesn't just all fall off. So you've got all these forces that are constantly inside your body, as well as all the ones that are applied to your body as a whole that stop you from accelerating into the ground whilst simultaneously trying to accelerate you into the ground, and so on. So there's constantly heaps and heaps of forces going on. So you might just think, well, there's too many forces. It's just a big mess. So part of the goal of our problem solving, the physics part, before we get into the math, part of the goal is to figure out which ones are the relevant ones. Do we care about the acceleration, the force due to gravity? Does that matter for this scenario? Does the normal force matter for this scenario? Does a push force, is there enough friction for us to care about that one? So going through and figuring out what's actually relevant is a big part of the physics for the problem solving approach with forces. Lesson 10, I believe, is going to be entirely on problem solving. I'll work through a few examples and we'll discuss this in a bit more detail. We'll go through and we'll actually think, which forces do we care about? So force is a vector. It's got direction determined by the interaction. If you push in a different direction, or if the center of gravity moves, then that's going to move the direction of the force due to gravity, and so on. So the force direction is pretty obvious, pretty easy to understand. Force magnitude. The force magnitude is the strength of the push or the pull. I already mentioned if you push harder, you get a bigger force. So we want to define that magnitude. Direction, we already know how to define. It's literally a direction. You can choose an angle, you can choose a coordinate system. However you want to define it is fine. We understand there must be a direction. For the magnitude of the force, we need a unit. We need some way to agree with other scientists what we mean by a certain strength of force. So the unit that scientific community has agreed upon is called the Newton, after Sir Isaac Newton. And we use the symbol capital N for that. So the unit is capital N, but it's actually a derived unit. As we'll see, the unit itself, 1 Newton, is actually equal to 1 kilogram meter per second per second. So that might not make a lot of sense yet, but we will talk about that a bit more with Newton's laws in the next lesson. Oh, and the other thing I didn't mention that is written on the top of that slide is the symbol F. So when I talk about symbols for a quantity, that means the symbol in the equation. When I talk about a symbol for a unit, that means the letter or symbol that you put after the resulting value for that quantity. So F would be in our equation. We'd have an equation with F in it. That's the force we're going to find. That would be our symbol for the force value itself. The symbol N tells us the units of the numerical result we get for that force value. So hopefully now you understand what forces are in general. They're just pushes or pullers and they're vectors, and they have directions and magnitudes, the magnitudes being given in newtons. Now we want to talk about free body diagrams. So when we've got a scenario, in this case we're pushing a box. We've got a scenario and we want to sketch this because a graphical representation is a really good way to approach a lot of problems. It's not always the best start, but in general, you're not going to go wrong if you do draw a little diagram. So we want to draw a little diagram of a box and someone pushing it, and that's easy enough. You can draw a square for the box. You might draw a hand in there, or you might just sort of draw a circle representing the hand, and that's fine. But as soon as you start to get to more complicated scenarios, what if you've got a car or a rocket ship? Are you going to actually sketch that vehicle? Are you going to sketch a tree? What are you actually going to draw when you have to draw a diagram of something complicated? What if you're talking about a bridge and you want to draw a diagram of the forces on the bridge and figure out what's happening with that? Are you going to sketch the whole thing? Are you going to include the landscape? How complicated is your drawing going to get? And the answer is we don't want it to get complicated at all. We want to simplify it as much as possible, and that's what a free body diagram is. A free body diagram is a representation of a scenario, but what we do is we just draw a dot for the object. We don't bother trying to sketch it. Some people will try and draw simplified versions, or they might turn every object into a box or a circle or something. Generally, the simplest approach is just to make it a dot. Right? So your object, in this case, we're talking about a box, you just draw a dot. You could call it the box if you want, but it's just a dot and it's just the box. Then you draw the forces as vectors. We already know how to sketch vectors, so you draw the forces as vectors coming off the object, so off that dot. If you know the magnitudes of the vectors, it's a good idea to keep them roughly to scale. Sometimes you don't know the magnitude, you only know the direction, in which case the length of the vector isn't that big a deal, but you still want to try and get those directions correct. So that's the idea of a free body diagram. I'll give you an example now, but the idea is that you don't need to be able to draw. You don't have to be an artist to create a diagram of the physics, because all we really care about when we're talking about the physics is what are the forces applied to each object and what direction are they going in, so that we can try and figure out what we'll meet shortly as the net force. So here's an example of a box on a table. You could go and draw something like the image on the left, and even if you're capable of doing that, it's kind of a waste of time, right? There's nothing more that we get out of that piece of diagram than we do from just the free body diagram on the right, which is just a dot labeled a box. You don't have to label it box because it's the only object in the system that we're actually caring about. So going back to our definition between system and scenario, you can see that the scenario is a box sitting on a table. The system, though, is just the box. We don't care about the table. We're not watching the motion of the table. We're watching the motion of the box. So the system itself is just the box, in which case, if you already know the system is the box, then labeling your dot as box is a bit redundant because we already know the system is the box. And what we have is the support force. That's the force from the table that's stopping the box from falling into the earth. And we've got the gravitational force due to the earth that's, excuse me, that's trying to make the box fall into the earth. So those are the only two forces on the box. As I said, we'll learn more about those forces, the common forces, in the next lesson. But that is a free body diagram, just a dot with some arrows on it. Writing support force and gravitational force is pretty cumbersome though. When we've got two forces, it's not too bad. If we get into a scenario where we've got a dozen forces acting on one object, then writing the full name for every force is going to be it's a waste of time, right? It's going to make the diagram messy. It's going to be too much clutter in there, and it's not the most efficient way we can do it. And the whole point of free body diagrams is to efficiently convey that information visually. So instead what we do is we label our forces using subscripts. So you remember subscripts? We used them with velocities and positions and things with little i's and f's for initial and final, or occasionally we used P for peak or M for midpoint. You can make up your own subscripts, it's fine, right? You can use them. It's good to define them if you make your own one up, but if you want to use common ones, then you don't have to define them. So what we have is a whole bunch of different forces. Again, next lesson we're going to talk more about, lesson after, we're going to talk more about common forces, and we will introduce a few suggestions for these sorts of common subscripts. But you can just use F with a subscript W for the weight force on an object. Some people do just use a big capital W. Personally, my preference is to use the F for any force and then a subscript to say what the force is. It just reminds everyone involved, including yourself, that it is a force. Right? So the weight isn't some magical other quantity, it is just a force. It's a force due to gravity, so force with a subscript W, force, weight force, right? And then friction force, we're going to learn about that again in a couple of lessons. Again, some people just use the letter F, a lowercase f for friction. Personally, again, preference is the big F with a subscript little f to say it's a force, and then the subscript says, but it's a force due to friction. Normal force, F with a subscript N. Some people call it support force, so you also sometimes see F with a subscript S. but as we'll learn when we talk about these forces, normal force is a better name for it because it is descriptive of a certain property of it. So I recommend sticking with N for normal force. Push force, you might do F with a subscript whole word push. You might write the whole word push in there, or you might just use P. Again, it depends on the scenario. If you've got other things that also have P's in their name that are resulting in forces, you might not want to just use FP. You might write the whole F push, but it's up to you. And then finally, net force, which we're going to define in a bit in this lecture. I recommend using the whole word net because that is essentially the most important result of our diagram. So if you know the net force, then identifying that very clearly is very important. So writing F net is the best approach there. So as I said, you can choose your own subscript, try and be consistent and logical, but you can choose your own ones. And the idea is just that we can draw our diagrams and keep it simple. So that becomes something like this. This is a free body diagram of a box being pushed along a rough surface to the right. We don't know the whole scenario. All we've been said is it's on a rough surface, so we don't know what object it's on, but it doesn't matter because our system is just the box. So we have one dot because there's only one object in our system, one dot, we don't need to label it because obviously it's the box. We've got our weight force going down, Fw, our normal force going up, which is Fn, our friction force going leftwards, Ff, and our push force going rightwards, F push. And you can see I've drawn the net force, F net, on there in a different color. You obviously can't always draw different colors. If you're doing it at home with a pen or pencil, you might just have the one color. So making the arrow slightly more obvious, or circling the F net or underlining it or something is a good idea, just to really emphasize that F net if you do know it. So what do forces do? Excuse me. We've talked about the idea that forces change motion somehow. Forces cause an acceleration. So what we're going to do now is a bit of a hypothetical. We're going to think about a scenario and imagine what would happen. So our hypothetical scenario is a lonely object out in a very empty region of space. The reason we're out in space, in an empty region of space, is that we've got no nearby planets or stars. So there's no gravitational force on this object. So there's no default force. On Earth, we've got a default force of weight force. No matter what an object or person or anything is doing, if it's on Earth, it's going to be subjected to gravitational force due to the attraction with Earth itself. So we've always got this one force at least that we have to consider. If we go out into space, far enough away from all planets and stars and everything, that there's no noticeable gravitational force, then that means that our default is no forces at all, and that's good for our little hypothetical scenario. We've also got no air out in space. Space is a vacuum. We're going to define air and vacuum. Define air. You know what air is. We're going to define what a vacuum is in relation to air in the second half of the course. So we've got this object. We've got no way for it to experience any friction because there's no other objects. We've got no way for it to experience gravitational force because there's no stars or planets or anything. So we just have an object sitting there. What we're going to do is define a frame of reference in which the object is initially at rest. So our object is the origin. Doesn't really matter what direction X or Y is, don't care. All that matters is the origin is the object. We'll say that X is the direction we're going to push it in because that's what we're going to move towards, but it doesn't really matter right now. And if we just watch that, if we don't push it, we just watch, we don't do anything to this object, what's going to happen? Hopefully, what you'll agree is that the object would just stay exactly where it is on this frame of reference. There's no reason it would spontaneously start moving at a different velocity. So if it's sitting there at rest relative to this frame of reference that we've chosen, there's no reason it would suddenly start moving in any direction. We don't get velocity spontaneously changing. It just doesn't happen. The accelerations only ever occur as a result of a force. If we push it, it'll start to move. But if we do nothing to it, if we just watch it and there's nothing ever interacting with it, then how would it start to move, right? So no force means no acceleration. If we then push on the lonely object, then the object will move in the direction of that force. You push on an object, it's going to move the way you push it. That's hopefully intuitive from everyday life. You push on something, it'll move in that direction. That means its velocity is changing. If its velocity is changing, that means we're getting an acceleration. And the acceleration, as we already expect, is going to be in the direction that we push it. So you push something, it's going to move in that direction. What if you push a bit harder? If you give a bigger force, apply a bigger force to our lonely object, then it's going to accelerate more in that direction, right? The velocity is going to change more, so that's a bigger acceleration. So again, hopefully this is all fairly intuitive. We're just going into our hypothetical scenario to try and remove everything else, so we don't have to worry about friction and gravity and all of that. To keep going with our little hypothetical scenario, we need to bring in a new concept called mass. Fortunately, mass is something that people are generally aware of from everyday life, because mass is simply the amount of matter that makes up an object. Unfortunately, in everyday language, people tend to call mass weight. So when you talk about the weight of something in kilograms, that's everyday language. When you're in science discussions, science conversation, you need to use mass for the amount of something in kilograms. So when you're dealing with kilograms, that's a mass. In physics, weight is actually a vector, it's a force. We're going to meet that in the next, in a couple of lessons, how to calculate it. A lot of you probably already know it's just mass times the acceleration due to gravity. But weight is a vector, so it's a force. You need to be very clear about the difference between mass and weight. So mass is the amount of something there is, and that's measured in kilograms. So kilograms is literally just a measure of how much of something there is. We will define mass, but we're not going to do it until probably, I think it's lesson 18, second half of the course, we're going to start looking at matter a bit more closely. For now, we're already generally familiar with the concept of kilograms, but unfortunately, we have this everyday confusion between the mass of something in kilograms and how much weight it has, how heavy it is, which are sort of different concepts. So try and keep in mind that for now, mass is just an amount of something. It doesn't matter if it's on Earth, on the moon, out in space where there's no gravitational force at all. Their mass is just constant. It's just how much of the matter there is that makes up this object. Mass is a new dimension. So we've got dimension capital M. If you remember the dimensions L for length and T for time, then that means that the dimension M is a new one. And for force, which we already saw that force and acceleration, we saw force results in acceleration. So it's sort of, you might guess that the units are going to be something like mass times length divided by time twice, divided by time squared. We also will recall the units were kilogram meters per second, and that agrees with those dimensions. This again, when we define a couple of our Newton's laws, this will be very clear that this makes sense. So now going back to our hypothetical scenario, but now imagine we've got two lonely objects. One of them has a bigger mass than the other. So one of them has more stuff in it, more matter than the other one. If you apply the same magnitude force to each of these two different objects, what do you expect the result to be? Right? What do you think will happen? Hopefully you agree that the larger mass, so the one with more mass in it, will move less. Because if you push something that's got more mass in it, then it's not going to move as quickly, as easily as if you push something that's really, I was going to say light. It's getting confused between mass and weight again, but something with less mass in it. Right, so hopefully this is intuitive, that if you apply a push force, the same push force, to two different objects, the bigger one, the one with more mass in it, is not going to accelerate as much. It's not going to end up moving as quickly. So a bigger force a bigger mass, I've highlighted a bigger force there, which is why I started to say bigger force. A bigger mass will accelerate less for the same force than a smaller mass would. So all of these hypothetical discussions that we're having about these lonely objects, we're going to cement them a little bit in the next lesson with Newton's laws, because these are sort of building up to Newton's laws. Speaking of Newton, let's define that Newton. We already said that the Newton is in kilogram meters per second, so it had those units. But how do we define a Newton? We know a meter, we can get a ruler, and that it's agreed upon length is 1 meter, and agreed upon second is in our stopwatches, in our phones, and on our clocks. And there is a definition for that, but we're not going to get into exactly how that is defined. But there is an agreed upon definition for a second. We all know how long a second is. And now we've got the idea of a Newton. Actually, there's kilograms as well. The kilogram is an agreed upon amount of stuff. There used to actually be, I can't remember if they still do it this way. There used to be just a 1 kilogram block of substance, I don't know what it was, that was kept in a safe lab, and that was the world's definition for a kilogram was this mass that they had. Anything with the exact same mass was 1 kilogram. But obviously we have scales and other ways to determine masses. So the Newton needs some way to define it. And that was agreed upon, that a Newton would be the force, 1 Newton is the force needed to accelerate a mass of 1 kilogram by 1 meter per second per second. So that's the definition. So 1 Newton equals 1 kilogram being accelerated at 1 meter per second per second. Now let's go back to our lonely object. We've just got the one hypothetical lonely object now. We've got rid of the other one. Let's apply 2 forces to that object instead of just 1. What happens if we apply 2? Well, if they're equal and opposite, we would expect the object won't move. You can imagine this as 2 people pushing exactly the same amount in exactly opposite directions to each other. So there's an object and they're pushing each equally, one that way, one that way. The object's not going to move. The 2 people are just going to effectively be pushing against each other and nothing's going to happen. That object isn't going to move. So if the 2 forces are the same, it'll be just like there was no force and the object is not going to accelerate. If one force is bigger than the other, then you would expect that the object would move in the direction of the bigger force. So the person that pushes harder is going to win, in essence, and move the object the way they're pushing it. So in that case, if one of the forces is bigger, the object will be accelerated in the direction of that force. And this leads us onto the concept of a net force. So when we talk about objects being subjected to a lot of forces, we don't want to just have to consider every force individually. What we want to know is the overall total force that's being subjected to, that's being applied to that object. And we call that the net force. So the net force is just the sum of all the forces. If the lonely object is subjected to a leftward force of 2 newtons and a rightward force of 1 newton, then it would move exactly the same as if it was just subjected to a 1 newton leftward force. Right? 2 newtons to the left, 1 to the right, that's the same as just 1 newton to the left. So that's our net force. Now remember that forces are vectors. So force addition is always vector addition, which means we need to be considering direction, not just magnitude. So a couple of examples. Examples, net force in 1 dimension. We have a 1-dimensional vector, so it is plus or minus. That is sufficient for our direction. The diagram on the left, we've got force 1 is minus 4 newtons. So I've called left negative and right positive. That's my personal default format. You're free to define it whichever way you want, in which case the pluses and minuses in my examples there would just be flipped. But if we've got left negative, right positive, then the left-hand diagram, we've got negative 4 left, positive 4 right. So add them together, 0, easy. The next one, we've got 3 newtons to the right and 1.5 newtons to the right. So I've defined them both as positive. Add them together, we get 4.5 newtons to the right, easy. The last one, we've got, again, 1 left and 1 right, but now they're different magnitudes, but it's still 1-dimensional, so it's still simple math. Minus 2 plus 4.5, we get plus 2.5. Then we've got the idea of 2 dimensions. 2-dimensional forces are just our vector addition that we've already seen. So you may want to decompose vectors. You may do it graphically if they're simple enough and you're not worried about getting a really precise answer, but you do need to remember that they are vectors. You need to take their direction into account. So if we've got 4 newtons in the positive x direction, 4 newtons in the positive y direction, so you'll notice, hopefully, in this case, I've made the frame of reference is, I haven't defined it, but clearly one of them is positive to the right and one of them is positive downwards. Again, personally, I tend to keep x being left, right, and y being up, down, but y, as you'll notice from, remember hopefully from the gravity and free fall and all of that kind of stuff that we did with kinematics, y can easily be positive or negative, up or down. I don't have any preference there. Left and right, I don't know why, I just tend to call left positive, left negative and right positive. But there's nothing to stop you flipping it. So I've called positive x to the right, positive y downwards, and that means that our net force is just plus 4x plus 4y newtons. That's perfectly acceptable to leave it in that component form, to say it's 4x and 4y. That's fine. You can, of course, find the magnitude using Pythagoras, the square root of 4 squared plus 4 squared, and you can, of course, find the angle. In this case, really simple because we can see that it's equal amount left and down, so it's going to be an angle of 45 degrees below the horizontal. But again, SOHCAHTOA, find your angle, Pythagoras, find your magnitude. Sometimes, or a lot of the time, we will want to know that exact magnitude, so you will have to find the magnitude. But I'm not going to repeat all of the process here because that's just math and you already know how to do all of that. The last term we want to define is equilibrium. Equilibrium is used in a lot of scientific senses and occasionally in daily life, but it always means that something is balanced. Equilibrium is just a way of saying that something is balanced. For physics, and specifically at the moment while we're talking about forces, equilibrium for forces simply means that there is no net force. It means that all the forces, no matter how many forces there are, they all sum to zero. So when any object is at equilibrium in our force discussions, we mean there is net force of zero. So if we're talking about forces and someone says net force is zero, you know it's at equilibrium. If they say it's at equilibrium, you know net force is zero. And that's the end of this first lesson. As I said, there wasn't too much math. There was a recap of vector addition, but that's not new. There's nothing new about that. We've already met the idea of adding vectors, so there's nothing new there. What we did do was hopefully get an understanding of what forces are. Forces are vectors, and they are just pushes or pulls. They're a way that we represent a push or a pull on an object scientifically, because obviously, as we talked about with motion, we need some way to agree upon these sorts of quantities and these sorts of interactions that everyone that deals with physics will all agree on and all understand. So we have to define forces in some way, and that is just a push or a pull, either by contact or at a distance. And then we draw free body diagrams to represent those forces being applied to any specific system. We did some hand-waving hypothetical discussions around how the forces result in the motion. That's what we'll solidify in the next lesson with Newton's laws. Newton's laws basically take that stuff we were talking about in our hypothetical scenario and formalize them into some laws. And then the one after that will meet the common forces, talk about weight and friction and all of that. And as I said, net force is just equilibrium. It's zero. Net force is zero. So that's the end of this first lesson on forces. We do have a lot of work to do with forces. Just about everything we do in this course is going to come back to forces. In the second half of the course, even once we've finished with this force section, we'll be coming back and we'll be looking at things that result in forces in different ways. So you really do want to get to grips with what forces are and how we work with them.